All right. Solving problems is fun. All right, so let's get into it here. So this is the problem I asked you to take a look at. And we're going to start with A. So in A, we've got an HDI of 1. We have a chemical shift of 1.09 ppm, 6 protons, which gives you a doublet. 2.2, we have 3 protons, gives you a singlet. And then at 2.58, we have 1 proton that gives you a septet. All right, so let's start with, does anybody recognize any of the alkyl groups that we covered, the 3 alkyl groups, an ethyl, a tert-butyl, or an isopropyl? Let's see if we can eliminate one of those first. Anybody see any of those groups? So remember, we covered ethyl, isopropyl, and tert-butyl. Yeah, somebody put an isopropyl, absolutely, right? So that would be these 2 here. We have a doublet that integrates for 6 protons and a septet that integrates for 1. So that means we have an isopropyl group in our compound. Yep. And let's see, we also have 3 protons that give you a singlet. The only possibility when you have 3 protons that give you a singlet is that you have a methyl group. That's the only possibility. But the fact that this methyl group is a singlet tells you that it's not split by anything. That means it's also attached to a carbon that has no protons attached to it. Okay, no protons attached to it. So now we've got 2 parts, and we've taken care of what? 1, 2, 3, 4 carbons. We've got 1 more, so 5. So that means the 5th carbon has no protons attached to it. And we've also taken care of, let's look at the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means we've taken care of all of the carbons, all of the hydrogens, and we just have the oxygen, and we have an HDI equal to 1. So that means that the carbon that has no hydrogens attached to it has to have a double bond to an oxygen, like that. So it must be a carbonyl. So the only way that we can put this together, there's only one possibility, is to take this isopropyl group. Okay, just let me eliminate some of the spinach that I have written here, is to take that isopropyl group and move it over here like that, and that gives you the compound. So this is called isopropyl methyl ketone is what you would call this. Give me a thumbs up if that makes some sense to you. Anybody with me on that one? Okay. All right, so that's how we put that together. Let's take a look at the next one. We've got C5H12O. This one has an HDI equal to what? What's the HDI equal to in this compound? It's 0, isn't it? Thank you. Good. Okay, so let's go with the ethyl, tert-butyl, and isopropyl. Does anybody recognize any of those in here? Do we have an ethyl or a tert-butyl or an isopropyl in this compound? Yeah, we have an ethyl, don't we? Right? Sean says there's an ethyl because we have a triplet that integrates for 3 protons, and then we've got a quartet that integrates for 2 protons. So that tells you that you have an ethyl group in the compound somewhere. So that takes care of that. Excuse me. Then what else? It says we have a singlet that integrates for 6 protons. So the only way you could have a singlet that integrates for 6 protons would be to have 2 methyl groups and for them to be attached to a carbon that has no hydrogens attached to it. That's the only way that that could exist, right? 6 protons. So that means they have to be attached to a carbon that has no hydrogens attached to it whatsoever. So there's got to be some symmetry there. I'll just leave it like this, okay? What else? You've got at 2.24, you've got a singlet that integrates for 1 proton. Well, let's go back to the HDI. If you have an HDI equal to 0 and you've got an oxygen in your molecule, well, what's the only possibility? Is that you could have either an alcohol, right, ROH, or an ether, which is ROR. But we don't have an ether because if we look at the table of chemical shifts, so let's go back here. Let's go back to the table of chemical shifts. So it was right here, okay? And if we look at, a bond to an oxygen. So we have methyl ketone, aromatic, alkyl halide, alcohol. We see that an alcohol has a range of 2 to 5 parts per million. So that's a bond to an oxygen, right? And so an ether should be somewhere similar to that, but you see that we don't have two sets of protons that have a chemical shift that high. So that means it must be an alcohol. So if we go back to the problem, that means that we have an ether in the compound. So we'll circle, it is an ether, and it is, or sorry, it is my mistake. That means we have an alcohol in the compound. It is not an ether. So that means we have an OH group. So now we just tie all of these parts together. We've got a carbon that has no hydrogens attached to it, but it's got 2 methyls. We have an ethyl group, so we could put that in like this. Okay, and then we have an OH group like that, and that is the final compound. That's it. That's the only way we could put that together. If you drew a bond line structure, it would look like this, is what the compound would be. All right, and the one on top, if you drew the bond line structure, that would just look like this. All right, so there you go. There's a little practice on using some chemical shifts and some multiplicities or some splitting and some integration to solving a couple of NMR problems, proton NMR problems. But in order to tackle questions like 15.39, we still have to cover the topic of carbon-13 spectroscopy. So I'm going to go back to the slides, and we're going to talk about carbon-13. So we're finished with proton now, and we're getting into carbon-13. So I just want to remind you of one thing before I get it really deep into carbon, is that when we were talking about proton, okay, with proton NMR, we said that we looked at splitting, or n+1, right? So we looked at splitting, we looked at integration, and chemical shift. Okay, well, in carbon-13, so in carbon-13 NMR, which is what we're dealing with now, the only thing you're going to look at is chemical shift. Chemical shift only. Okay, so that's why this section is a lot shorter, because it's the only thing that we talk about is chemical shift. We don't talk about any n+1, and we don't talk about any integration. So NMR signals are really strong for proton, and that's because hydrogen 1 is by far the most abundant isotope of hydrogen. But remember, carbon-13 is only about 1% abundant. So that means if you run a sample that's got, 1 gram, so that, or let's say, 1 gram, that means that only 10 milligrams of it are, 10 milligrams of it is going to be, it's going to have carbon-13 atoms, right? So it's 1% abundant. And so you need to either have a much more concentrated sample, which is ideal, okay, so they have a really concentrated sample, or you need to run a longer experiment, have a more sensitive receiver coil. That just means you've got to take more time to run the experiment. But again, in proton NMR, we looked at shift, splitting, and integration. And in carbon-13, the only thing we look at is chemical shift. Oops. Nothing else but chemical shift. It's the only thing we talk about, no integration, none of that stuff. So if you go over to the table, okay, and again, this is the table I give you on the quiz, you'll see that for carbon-13, the only thing I give you is chemical shift. But you probably noticed that the numbers are a lot bigger here. Instead of being 0 to 12, right, which is what it is for proton, right, for proton, the range is 0 to 12 parts per million. The range for carbon is around 0 to 220 parts per million. So much wider range of frequencies for the absorbance of carbon-13 nuclei. Let's go back to the notes here. And so in carbon-13, you can get proton and carbon-13 splitting. But what happens is the splitting is so complex that usually you can't even read the spectrum. And so what we do is it says to elucidate the carbon-13 and make it easier to determine the total number of carbon-13 signals, the carbon-13 are generally decoupled. So what that means is that you decouple the carbon from the proton, and that way you don't get any splitting for the carbon. You just see a bunch of singlets, Okay, that's all you see is a bunch of singlets. Now, one thing that I do want to mention briefly is there is another experiment called off-resonance decoupling. So I'll write it down here. Off-resonance, you can scribble this down, decoupling. And this is in your textbook, decoupling. In that case, if you run a methyl group, the carbon shows up as a quartet. If you have a methylene, okay, you can imagine this shows up as a triplet. And if you have a methyne, that shows up as a doublet. So a methyne shows up as a doublet. And a quaternary carbon shows up as a singlet. So singlet. This isn't even in our textbook. I don't know if he puts any problems, okay? But very rare. But these are sometimes in the ACS, and they're also sometimes in MCAT study material. So I will show you an example of off-resonance decoupling before we're done the chapter. But usually we don't do that. We usually just make a completely decoupled spectrum, which we call broadband decoupled. So this is called broadband decoupled, and that just gives you only singlets. So everything is a singlet. And then if you do off-resonance decoupling, you can see the splitting by the protons. But again, the reason why, and if you're wondering, well, why don't we do this all the time? Then you could always tell what a quartet or what a methyl is and what's a methylene, et cetera. The reason why is because it's usually very difficult. It's usually unreadable, okay? So the vast majority of spectra, we run broadband decoupled experiments, and we get only singlets. All right. So again, different resonating frequency for carbon-13 atoms as opposed to proton. And so that's why we have a huge range of 220 to 0 parts per million. And each unique carbon, just like each unique proton, will give you a unique signal or a different signal. And again, the same thing, we have to take into account planes of symmetry and axes of symmetry, which cause carbons to be chemically or electronically equivalent. It means the same thing. So now if we look at these three compounds, they all have the same molecular formula, right? So it'd be very difficult to use MS. They're all just aromatic, xylene. So it'd be very difficult to differentiate between them using IR or MS, but we could use carbon-13. And if you're looking at these and going, well, didn't you just talk about these and say you could use proton? You could use that too, but it's just showing you could also use carbon. So the first compound has 4 signals, and the one in the middle has 5, and the one at the end has 3. Now notice that even the carbon that doesn't have a hydrogen attached to it, it still shows up in the carbon-13. All right, so you've got to be aware of that. Now the chemical shifts in carbon-13, the first thing you'll notice is that if you have any kind of sp or sp3, so sp and sp3 hybridized carbons, those fall in the range of 0 to 100 parts per million. sp3 are usually the least deshielded, so those are 0 to 50. So that would be your methyl, methylene, methine groups. And then anywhere between 50 to 100, there's a lot of things that could be in there, like an alkyne, bonds to nitrogen, bonds to oxygen. And then we get up into sp2 hybridized carbons. So those go all the way from 100 up to 220. So this is sp2. Aromatic fall over a huge range. I'd say 110 to 170, something like that. And then once you get up into like 160 up to 220, that's when you have carbon atoms that are attached to or in carbonyl groups, so carboxylic acids, aldehydes, ketones, amides, and all that stuff. But again, you can see there's a lot less information in the carbon table of signals. Now, again, I give you an abridged version of this table. Okay, I don't give you this table specifically. The table that you're going to get for your quizzes is going to be this table down here. So I don't write down what the structure of an alkane, an aryl, a carbonyl. I just kind of give you a generic range here. Okay, so that's the version of this table. So you cannot bring the table from the book. You bring this table. Okay, you print this page out. All right, let's go back into the slides here. And now that we've covered that, we're going to cover one more section before we take a look at some problems that involve carbon. It says carbon-13, like I said, we do broadband decoupled experiments, which give us singlets, unless you do the off-resonance coupling, and I told you that's really, really rare. So it doesn't tell you anything about the number of hydrogen atoms attached to each carbon. So we actually have a workaround for that, and it's called a DEPT experiment, the distortionless enhancement by polarization transfer. You don't have to remember the acronym, what it stands for, just a DEPT experiment. And there's two types of DEPT experiments. The first one is called a DEPT 90, okay? And a DEPT 90, the only thing that shows up is methynes, okay? So methine signals are the only thing that shows up. Then you can run what's called a DEPT 135, and in a DEPT 135, what you end up with is something really interesting, is that the methynes and methyls are pointing up. So any methyl or methine is going to be pointing up like this, and the methylene, they're actually pointing down, okay? So if you run a broadband decoupled, a DEPT 90 and a DEPT 135, you'll be able to identify every single carbon in the spectrum as being either quaternary, meaning it's got no hydrogens, methyl, methylene, or methine. Okay, you can tell all of them. And if you're wondering, well, how do you do that? Well, again, in the broadband decoupled, you get everything. Okay, you get a singlet for everything. But then once you run a DEPT 90, you can identify which ones are the methines. So now you've figured out those. Then when you run the DEPT 135, you can determine what was a methylene and what is a methyl. Okay, and you can differentiate between the methyls and the methines by comparing it with the DEPT 90. And then whatever didn't even show up at all in any of the other two experiments, those are your quaternary carbons. And there you go, you've identified everything. So all you have to do are these three experiments, and then you don't have to do off resonance decoupling, an off resonance decoupling experiment. Okay, don't have to do it whatsoever. All right, so pretty cool set of experiments. I'm not going to cover the section on MRI. I'll just leave that. The MRI will be an FYI. Don't ask any questions about that, so you can take a look at that if you want. So now what I want to do is I want to go back to that set of problems that we were doing before, and I want to take a look at, why don't we take a look at a couple of problems here, and why don't we start with this problem, 15.39D is where I want to start. And we're going to jump around on some of these problems, and trust me, I have a method to my madness here. So 15.39 says, for each pair of compounds, identify how you would distinguish them using either proton NMR spectroscopy or carbon-13 NMR spectroscopy. You know what, let's just start with A. Let's make it simpler. We'll start with A. Okay, so if I'm looking at A, could anybody tell me how many signals would you see for this compound in the proton NMR? How many signals would we see for this compound? And it's not a trick question or anything. Let me bring up the chat here. I can't see it. There we go. Yeah, somebody says that you'd see a total of, did I say for the proton? I think I said for the proton. How many signals would you see in the proton? You'd only see two, right? You'd see two signals for the proton. So let's do proton NMR. NMR, you would see two signals. Okay, so let's see what they would be. We'd have this, and this is a chemical equivalent of this and this. Then we also have this one, and this one, and this one. And again, the reason why those are all chemically equivalent is because you have two planes of symmetry. You have one here, and then you have another one running this way. So two planes of symmetry, and therefore we only get two signals. Everybody with me on that? So now let's back up, and how many signals would we see in the carbon-13? So let's do carbon-13 NMR. How many signals would we see for the carbon-13? Okay, so somebody says 4. I think that sounds reasonable, right, Sean? Because this carbon and this carbon are chemically equivalent. Then we have this carbon and this carbon are chemically equivalent. Then we have these 4 carbons are chemically equivalent. And then we have these 4 carbons that are chemically equivalent. So that's 4 different colors that I've used up. So it's a total of 4 signals. 4 signals. Remember, in the carbon-13, even a carbon that has no hydrogens attached is still going to show up. So now if we do the same exercise over here for proton NMR, are there any planes or axes or planes of symmetry in here, or axes of symmetry? There's none. There's no symmetry in this molecule whatsoever. And so for the proton, we're going to get a unique signal here, a unique signal here, a unique signal here, a unique signal here. I'm running out of colors here. You're going to run a unique signal here. I'll put different shapes, right? This is going to give you a unique signal. Then this is going to give you a unique signal. And then this is going to give you a unique signal. So for proton, you end up with 1, 2, 3, 4, 5, 6, 7, 8 different signals that you would get for this compound. So we would have a total of 8 signals. So my question to you is, in the carbon-13, could anybody just tell me how many signals you would see for this compound in the carbon-13? Exactly, you see a total of 12. Every carbon in here is unique, right? Every single carbon, I'll use my purple pen here again. Okay, every carbon in this molecule is unique. Maybe I could put an oval around one. I'm kind of running out of ideas here. Put a triangle around this one, and then we'll put maybe yellow highlighter on this one or something. But every carbon in here is unique. So you would get a total of 12 signals for this compound. I'll put here 12 signals, like that. So now that we understand carbon a little bit more, let's go over here and let's take a look at a compound where they give you a carbon-13 NMR spectrum. So this is what a carbon-13 looks like. It goes all the way from, I mean, this one doesn't go all the way down to 0, but it goes to close to 0, all the way up to 200 maybe, or 220, whatever, close enough, 200 in this one. But anyhow, you see that in the carbon-13, all you get is a singlet, right? You have a singlet here, so that's 30.7 ppm, right? This one is 35.8 ppm, so 2 singlets. Then you go here, you get a singlet here, 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 okay? And then here, so we have a total of, if I count them all up, 1, 2, 3, 4, 5, 6, 7 signals in the carbon. So we could scribble that down, that in the carbon we have 7 signals. That means we've got 7 types of carbons. Now look at this. They gave us a formula over here which says C9. So if it's C9, then why would we only get 7 signals? That means that there must be some symmetry in the compound somewhere, doesn't it? All right, there has to be some kind of symmetry somewhere in the compound. All right, is everybody with me so far? Symmetry in the compound if we only get 7 signals and there's a total of 9 carbons. Okay, let's see what other information we can get from the carbon. So remember that we said that if you were below 100, okay, below 100, that these were kind of your sp3 and your sp hybridized carbons, and then up here we said that these are all sp2 hybridized. Okay, now if I have a big bunch of signals in between, 110 and 160, something like that. Okay, so you see all these signals here. What does that suggest? Well, before we answer that, we still haven't looked at the molecular formula. The molecular formula says is C9H10O2. Could anybody tell me what the HDI is for this compound? Anybody tell me what the HDI for this compound is? Okay, yeah, it's 5. Okay, so the HDI is equal to 5. And so what does that mean? 5 double bonds, highly unlikely, right? Right, Ariana? Now, what do you see here? If you peek up in the proton, we have five protons around 7 parts per million, and then you have a bunch of signals in the carbon around 130, something like that. So what kind of functional group do you think we have in this compound? What am I trying to tell you? It means you've got an aromatic ring, right? Exactly. You must have an aromatic ring. So if I put this like this, okay, that means that there's an aromatic ring. Now, if it integrates for 5 protons, that means that the aromatic ring only has one thing attached to it because everything else is a proton, like this. Okay, 5 protons. Now let me go back to all the signals that I have in the red circle here. There's a total of 4 signals here, right? But that makes sense because this carbon is unique. These 2 carbons are chemically equivalent. These 2 carbons are chemically equivalent. And then this carbon is unique. So I've got a total of 4 carbons in the aromatic ring, okay, that are, a total of 4 signals from my aromatic ring is what I should have said. Now, let me tell you something that I don't think the textbook tells you, but I'll explain it to you. And if you're taking the lab with Mr. Geiger, he may have explained this to you, is that there's no integration in a carbon-13 spectrum, but you see how these 2 signals here are about twice as high as this signal and this little signal here? You see how they're almost double the height? You're like, well, they're even more than double the height of the one at 140. The reason why those signals are higher is because there's probably twice as many carbons. And so the 2 carbons that are twice as high, the ones at 128.8 and 128.4, those probably represent the red and the green ones because there's twice as many of those. So we would say this is probably the red one and this is probably the green one. Then I have the blue one, would be the one with the blue check mark on it. This one here is going to be more de-shielded because there's something attached to it. And then this yellow check mark here, that represents the yellow carbon. Okay, so again, peak height, can you always go off of that? No, but if it's twice as big, it probably means there's twice as many. All right, now we haven't addressed the other HDI because an aromatic ring only has an HDI equal to 4. We still have, so 4 from the aromatic ring, and then we still have 1 more. What does that come from? Does anybody know what that would come from? Where do you think that might come from? Keep in mind that there's 2 oxygens in here, isn't there? What does it mean if we have a carbon that has a chemical shift of about 180? This guy here. What does that mean? That carbon is attached to what? If you have a chemical shift of 180. Let's go back to the table. Okay, if you go back to the table here, if you've got a shift that's in between 150 and 200, so if you're at 180, that means you've got a carbonyl. You probably also noticed that there was a proton at about 12 parts per million. So that means we've got a carboxylic acid in the compound. So let's go back here, go back to the problem. Okay, so this is a carbonyl carbon. That takes care of the last HDI. So that means it comes from a carbonyl, right? And we know that this 1 proton here means this comes from the carboxylic acid. So that means we have an aromatic ring and we have a carboxylic acid. So we've taken care of everything except for these 2 triplets that each integrate for 2 protons, and these 2 singlets down here that are on sp3 hybridized carbons. If I have, you see how it's hard to see in the screen here maybe, but this one has 1, 2, 3 peaks, and this one has 1, 2, 3 peaks. So this is a triplet, and this is a triplet. Now, how can I have 2 triplets that both integrate for 2 protons? The only way that that could happen is if I have a CH2 attached to another CH2, and then they're both attached to different groups that have no protons on them, right? Because this one would be split by these 2, which would give you a triplet, and then these 2 would be split by those 2, which would give you a triplet. So again, the X and the Y, they have to be different than each other. So if we put that whole thing together, what do we have? We're going to have something, I don't have a lot of space here. We're going to have something that looks like this, where you have an aromatic ring, CH2, CH2, and then your carboxyl group is going to come off like this. So this must be the structure of the compound. Give me a thumbs up if you're like 65% of the way with me on this, because you will have to practice these on your own. All right, good. All right, there you go. So you see how we used proton and carbon NMR together to solve this problem. So let's go back here. And let's try another problem that involves just proton for a second, okay? So let's try one more. Try this one here. I've got C4H10O. So that means I have an HDI of what for C? Could anybody tell me what the HDI of this compound is? Scribble it down here. HDI is equal to 0. Thanks, Savannah. Great. So then let's look at the multiplicities. You've got doublet, multiplet, doublet, singlet. Well, if you've got 6 hydrogens that integrate for a doublet, that means that you've got 6 hydrogens that are attached to a methine. Or sorry, yeah, a methine. That's the only possibility, right? So those would have to be those ones here. Then if you've got 1 hydrogen that's a multiplet, we'll come back to that. Then if you have 2 protons that are a doublet, that means you've got 2 protons that are a doublet. So that means that they're attached to a methine, a methine, because they're only split by 1 proton. And then you've got 1 proton that's a singlet. It's got a chemical shift of 3.92. And you've got an HDI of 0. So it's either an alcohol or an ether. Those are the only possibilities. All right. So this is an alcohol, or ether. But we've only got one set of protons that have a high enough chemical shift to be attached to an oxygen. So it must be an alcohol. So if we put all this together, you can see that these 2 methines, those are the same methine. So if I just delete the circle like this and I move the CH2 up like this, right, I've got CH2, and then the only place I can put my OH group is here. So there you go. And the reason that this has a multiplet is because it's coupled next to 1, 2, 3, 4, 5, 6, 7, 8, right? So n plus 1 is equal to 8 plus 1, but that's probably not going to be, you know, a nonette. There's no such thing really. So it's probably just going to give you some kind of jumbled up mess of peaks, which gives you a multiplet. So we'll just put here multiplet like that. All right. So what I'd like to do now is stop the recording just for a second here. Stop recording.